afternoon, everyone. I want to welcome you here for this talk. I also want to welcome the future video viewers of this lecture. I'm Russ Kaflish. I'm the director of IPAM, the Institute for Pure and Applied Mathematics. IPAM is a national math institute located here at UCLA, sponsored by the National Science Foundation, and with the mission of promoting the interaction of math, both pure and applied, with other disciplines. This year, 2013, has been designated by UNESCO and other organizations as the Year of Math for Planet Earth, also known as MPE 2013, which you've probably seen if you've been watching the slides. Throughout the year and across the globe, an international coalition of math and science institutions has hosted activities such as lectures like this one, museum installations, and conferences, including a current 3-month program at IPAM on materials for a sustainable energy future. You can learn more about this program and public lectures here at IPAM from literature that's on the tables outside the theater. This afternoon's talk is part of a public lecture series sponsored by the Simons Foundation. At locations on 4 continents, these presentations focused on energy, climate, disease, and sustainability for the planet. This lecture is the 9th and final in a series, and on behalf of IPAM and our partners in MPE 2013, I want to thank the Simons Foundation for their generosity in funding these lectures. Now I'll turn it over to Joe Rudnick, who's the Senior Dean of UCLA's College of Letters and Sciences, who will introduce the speaker.
Thank you. This is a nearly full house. I'm very impressed. It's my distinct pleasure to introduce Emily Carter. This is a kind of a homecoming for her, as if you've been looking at the view graphs to pass away the time, you'll notice that much of what I say has already been projected in front of you. But Emily served on the UCLA faculty for 16 years, from 1988 until 2004. When, to our great misfortune and Princeton's very good fortune, we lost her to that institution, where she's now a professor of mechanical and aerospace engineering and also of applied and computational mathematics. Emily is, in addition, the founding director of the Adlinger Center for Energy and the Environment. And in addition, she holds the Gerald R. Adlinger Professorship in Energy and the Environment. Emily is a world-renowned computational and theoretical chemist. She's internationally recognized for her work, which combines just about every theoretical and computational tool now available for the study of chemical structure and reactions to explore the properties of complex and novel materials of profound practical importance. I mean, among the techniques that Emily has utilized and advanced are the density functional method, molecular dynamics, and Monte Carlo simulations, particularly kinetic Monte Carlo. She's enhanced our understanding of catalysis and the mechanisms leading to the failure of materials. She's also performed work on combustion dynamics, the many-body Kondo state, silicon etching and growth, and metal-ceramic interfaces. And her current research focuses on the discovery and design of molecules and materials for sustainable energy, including materials for the conversion of sunlight into both energy and fuels, for use in solid fuel cells, for use in the efficient combustion of biofuels, and for incorporation into the structure of fuel-efficient vehicles and into the walls of fusion reactors. Emily's work has gained her widespread recognition. She's a member of the National Academy of Sciences and also of the American Academy of Arts and Sciences. I got a list of her awards. It's quite extensive. I'm just going to mention a few. She received the 2007 Award for Computers in Chemical and Pharmaceutical Research from the American Chemical Society. She delivered the August Wilhelm von Hofmann Lectureship at the German Chemical Society, and just last year, she was awarded an honorary doctorate from the École Polytechnique Fédérale de Lausanne. I'd actually like to take the opportunity to inject a personal note into these remarks. I mentioned the density functional technique. I was actually in the vicinity, not exactly at its birth, but when that technique first took its first halting steps. I arrived as a graduate student at University of California, San Diego, about a year after the publication of the paper that my dissertation advisor, Walter Cohn, wrote with Pierre Hohenberg, and the same year as the publication of the Cohn-Sham paper, which laid the foundations of the technique that Emily has so masterfully extended and applied. At that time, the method was recognized as an elegant proposal for the investigation of many electron effects in the solid state. However, it was only through the subsequent accomplishments of creative scientists, such as Emily, that the density functional approach has emerged as an almost uniquely powerful approach to the study of correlation effects in many body systems. We humans, through the demands we now make on the world that sustains us, are rapidly bringing this planet to a point of crisis. Our hope for the future lies in our ability to adapt to the changes that we have brought about. The work Emily pursues will, I am sure, play an influential role in the intelligent and beneficial transformations that we must bring about to ensure that all the inhabitants of the world we now share will thrive in the coming century and in the millennia to follow. And with that, I'd like to ask Emily to come up to the stage.
Well, it's a pleasure to be here. It is a homecoming. I left 9 years ago, and I come back and I see the beautiful campus, and I see many beautiful faces of former students, former people I worked with, both faculty and staff, and it's really a pleasure to be back. And it's also a real pleasure to be here to see how IPAM has thrived. I like to feel that I had at least a little to do with its inception and involved in a little bit in the proposal and in the site visit and things like that that led to the birth of IPAM. And it's just wonderful to see how IPAM has thrived. So with that, let me take you on a little bit of a tour of the evolution in my thinking about why quantum mechanics has something to do with the future of the planet. And what you'll see is that the research that I do is fundamentally relies on quantum mechanics, and the research that I do is all about the future of the planet. And what I hope to do is to be able to give you a sense of the challenges that we face, and for the mathematicians in the audience who would love to see some equations, I'm going to show a few equations. Okay? And the rest of you can just go to sleep for a moment. So without further ado, I know that it will be impossible, especially for the people in the back, to read what's on this slide. So I'm just going to explain to you what it is. First of all, it's a beautiful document that is put together every 2 years. It's updated by Lawrence Livermore National Lab. It's called an energy flow diagram. And essentially what you're seeing on the left are the inputs for energy in the United States. And on the right are essentially how we use that energy. Okay, use or not use, as the case may be. There's a big gray box here which says rejected energy, and that's how much energy we waste. It's about half of all energy. It's a huge problem. If we look over here, actually, it's been, even since I have been paying attention, which has really only been over the last 7 years or so, that I essentially woke up after the 2007 report on intergovernmental, from the report on intergovernmental climate change report that came out in 2007. There was an update very recently that just made it even more clear that human beings are causing severe changes to the climate, and that is largely because of the burning of fossil fuels. And I started looking at these diagrams, and what I discovered as time has evolved is that the box sizes, which are not really to scale, but it doesn't really matter, but the big boxes, okay, over here, they all represent fossil fuels, things that are made of carbon that effectively, when they burn, emit carbon dioxide. And the problem, of course, is I'm sure probably everybody in this room knows that carbon dioxide is a greenhouse gas, and it's warming the planet. And don't let anybody tell you otherwise. The physics is correct, okay? So the point is here, there's natural gas, coal, and petroleum being oil. And those together make up 82% as of 2011 of our energy sources, okay? And the problem with that, and this is my own personal statement, but I think many people would agree, that essentially, because we use these non-renewable fossil fuels, I already said they warm the Earth, they also distort our international relations, okay? I think that's pretty clear. We've entered into wars that we might not have entered into because they would not have been in our personal interest if it wasn't for the resources that lay beneath the soil in the lands that we went to. In addition, they threaten the global economy. We know that oil prices, when they spike, have severe implications for economic growth. And so it's really a huge issue in terms of how we think about going forward, in terms of whether we continue to rely for centuries to come on fossil fuels, or whether we actively and consciously decide to move judiciously, not immediately. We can't turn a switch and immediately go off of fossil fuels, but work toward that. And that's, in fact, what mathematicians and scientists and engineers can help with, because we can't just go to the shelf and pick off a solution right now, not one that's economical. It's actually very cheap to pull carbon atoms out of the ground, okay? And so, which is what the fossil fuels are made of. So it's the case that we actually need to invest in technology solutions, in basic research, in mathematical techniques that will help us analyze the phenomena and the materials and the molecules that are going to get us off of this fossil fuel path. So this flow diagram is also really interesting because here, this green box, the light green box, when I first started looking at these diagrams, roughly, 6 years ago, that little light green box didn't exist. It says biomass. Biomass has now become large enough. Why? Because of corn-based ethanol. So we'll have something to say about that later. Up here are renewables, and you see solar here is these numbers, basically, this box is not to scale at all. I mean, the amount of energy that we produce from solar is far less than 1%. And so we're way below what you'd like to be able to do, and we'll talk about why. In fact, we'll talk about it now. So this is not a Lawrence Livermore slide. This is an Emily Carter slide. And it's a slide that I put together at the behest of a trustee at Princeton who was listening to me. He's a professor at the Harvard Business School, and he said, "You better put that on a slide." So here it is. My point by this slide is to show that there is no one silver bullet. There's no one solution. There are many aspects to this very challenging problem. And in particular, there's no solution that we can't just think about one solution for a particular period of time. So on this axis here, I have time. Notice I have no numbers. I'm not committing myself to anything, right? I'm just saying that in the short term, or the medium term, and the long term, there will be different kinds of solutions that hopefully by the year 2100, we will have solved the problem. That's an issue that, scientists are actually quite good about thinking long range, and mathematicians are good about thinking long range. And I wish our politicians were better at thinking long range. Because that's really what it's going to take. It's going to take investments in research and development in order to actually have all of these boxes be functional. So in particular, when we talk about energy, we have to think about fuels and we have to think about electricity. Okay, those are the two ways in which we use energy. So fuels, if right now, of course, as we said, they basically come from petroleum. That's where they come from. They're starting to come from biofuels a little bit, but it's still economically not viable. And of course, there is this other set of fuels that is right now, especially, I live in New Jersey, Pennsylvania is right next door. There's a lot of concern about hydrofracking to get natural gas. But the fact is that in the short term, the best way in which we can make a difference in terms of carbon emissions and reducing the worst ravages of climate change to come are to focus on energy efficiency, so that's why it's short term, in different sectors, as well as clean, very important, clean, hydrofracking of natural gas. And the technology is there. The way to do it cleanly, I believe, is there, and I'm not the only person that believes this. It turns out that Lisa Jackson, the former EPA administrator, has come to Princeton frequently because she's an alum of Princeton, and she believed that even though people may think that she's not have said that she's not industry friendly, it's absolutely not true. She's a very pragmatic person, and she believes it can be done. It can, in fact, be done cleanly. And cleanly means not just in terms of the injection fluids and the wastewater, but also in terms of people are concerned about what are called fugitive emissions of natural gas, which is also a greenhouse gas. In fact, a worse greenhouse gas than carbon dioxide. And so it has to be done, and it can be done cleanly. And in that way, the beautiful thing is that this revolution of hydrofracked natural gas has actually displaced coal. And coal, I like to say that the best form of carbon sequestration is to leave coal in the ground. Okay? So, you know, coal produces carbon dioxide at essentially twice the rate in terms of the amount of energy produced as natural gas does. So the more we can move to natural gas power plants and shut down coal-fired power plants, the more. We're already seeing it in the US. We're seeing a drop in carbon emissions, and it's fantastic. And it's what we really need to do in addition to, for example, having natural gas power plants that are paired with things like solar and wind. Why? Because solar power plants or wind-based power plants, the problem with solar and wind is that they are intermittent. You don't get electricity from solar if the sun's not shining, and you don't get electricity from wind if the wind isn't blowing. But natural gas power plants, it turns out, you can power up the turbines that produce the electricity fast enough that they can compensate. So I'm hoping we're going to see an industry that pairs natural gas with solar and wind. Until what? Until we get to these two, which are out here at long range. Why? Because they're incredibly hard problems to solve. One is grid scale storage. That's a very important thing that has to be worked on, and it has to do with essentially having a way to store the excess electricity that you generate from wind and solar to be used at night, to be used when the wind isn't blowing. And we just don't have good mechanisms for that now, and it's going to require good scientific research, including mathematical modeling, that gets us to that grid scale storage. Many aspects to that problem. And finally, fusion power. So I'll have something to say about that too. But fusion is potentially a complete game changer because it is not like nuclear power. I mean, I have say for nuclear power on here, but it's not like the nuclear power that you're used to thinking about. It does not produce high-level waste. It is not dangerous. And it involves feedstocks that every country on the planet has access to unless you're landlocked, okay? Because it involves seawater, deuterium from seawater, and lithium from the Earth's mantle. You have those two items, and you can have your own fusion reactor. Okay, sounds great, but it's not there today, and I'll tell you why later on. Okay, I could talk about this all day. You're getting worried because I'm only on slide 3, so let me keep going. So Professor Rudnick already mentioned my research portfolio, so I'll go over this fast. I have work that's been going on within a team of researchers that are both modelers as well as experimental scientists to look at the combustion of biofuels. We need to understand how do we burn them efficiently and cleanly. Here's a mock-up of the ITER project that's going up in Europe. And we work on the fusion reactor wall problem. I'll have something to say about that later. Fuel-efficient vehicles, photovoltaics, so that's solar cells, Photoelectrochemical cells, I'll have something to say about that too, for making, essentially for using the energy from sunlight to affect a chemical reaction. To make, for example, to split water, you may hear about that, to form renewable hydrogen, or to make a liquid fuel by taking carbon dioxide and water and sunlight and essentially running this reaction. There's a reaction going on here of burning the fuel and making carbon dioxide and water. Well, let's run it backwards and take carbon dioxide and water and make methanol. That's what this is. And methanol is a lousy fuel. But we know from other catalysis how to take methanol and turn it into gasoline. So it is a viable option, but we're not there yet. There's a lot to be done. And also, solid oxide fuel cells. This is a very clean way of using a fuel flexible fuel cell that basically replaces this combustion to produce electricity. What it does is takes in a fuel on this side, takes in oxygen on this side, and through electrochemistry allows one to generate an electric current. And so it's a very clean, efficient way of generating electricity. And I work on all of these together with my research group. Okay, so why applied math and computation? It's a decent question. Why not just go into the lab and measure everything? And of course, if you could, that would be fantastic, because that's reality. I mean, I will freely admit that, in fact, equations they're beautiful, but the proof is in the pudding in terms of actually making a measurement. So lab measurements provide an incomplete picture. And I have actually two pictures here. This is from my colleague, Ed Law. It's a turbulent flame that, and again, it's combusting a fuel. But really, we don't have very much idea at all about the microscopic aspects of that. How is the fuel burned? How does it react with oxygen? How does it interact with the transport of of the fuel and essentially how the fluid changes and moves and how the chemistry couples to that so-called fluid dynamics. And then this is so this is sort of on the molecular chemistry level. And then here's a nice picture from materials science showing high temperature oxidation of effectively steel, okay, of iron. And showing here you have iron down here, here you have an iron oxide, here you have another iron oxide, you have this final iron oxide shown in red, which is in fact rust, okay, showing the evolution to rust. But how does it really happen? And of course, what we'd like to do is prevent it from happening. And so in order to prevent it from happening, you have to understand first how it happens. It's a complex situation, very hard to look at in situ. And so basically, these computer simulations can help by filling in gaps. They fill in information gaps in windows that just don't exist in the measurement tools that we have available to us. They also help us offer interpretations of experimental observations. They also help us suggest new targets for design of materials or design of a fuel. So it's an extremely useful partner with experiment. So the question is, though, when you start thinking about mathematics of modeling something like this, we have to also be partners with the discipline of physics. We have to think about what are the physical interactions that are important to include in order to really faithfully be able to describe on a computer this kind of reality. So in fact, one thing that's really important is to be independent. What do I mean by that? Well, it's a lot of computer models that people use because they don't have a choice. Okay, lots of times, they end up fitting to experimental observables. And I view that as cheating, okay? I don't want to cheat, okay? I want to be able to actually produce a prediction on a computer that did not take in any information other than the identity of the element involved, okay? That's the ultimate goal. Now, along the way, there are approximations, but they don't take in information from experiment. And so as a result, I can have an experimental measurement here, I can have a simulation over here, and if they don't match, then either it means the experimentalist didn't know what they were measuring, or there's some physics left out. But if I poisoned this simulation by inputting information from the experiment, then I've muddied the waters. So that's why independence is so crucial in what we do. And so in order to do that, we have to start from the basic physical laws. And in the case of molecules, atoms, and materials, chemistry, and material science, what we have to start with is quantum mechanics, hence quantum mechanics and the future of the planet. Quantum mechanics, what does it provide? Well, I have a slide on that, so I'm going to show you. So I wish this was me, but it's not. But it starts with a fundamental theory, okay? So some little girl's reading this book, hopefully, and I hope there are many such little girls out there doing so. And that fundamental theory is governed by one very important equation. It's called the Schrodinger equation, and that's given there. So it doesn't really matter. It's an equation that if you solve it, it gives you two things. It tells you where the electrons are in space and what their energy is. And it turns out that those two things, where the electrons are in space is described by a wave function or an electron density. In this equation, it's the wave function because electrons behave like waves. And we need to know their energy. Because once we know their energy, those of you, if you think about it, it will tell us something about the stability of them, right? And so this equation gives us that information. It's a beautiful equation, and it's essentially useless. Why? Because you can only solve it precisely, exactly, for one electron. And there's only one element in the periodic table for which there is only one electron in its orbit, and that's the hydrogen atom. So that's really useless. So what you have to do is take that equation and be clever about how you approximate the description of the wave function. And so what you do, and this is now completely schematic, the equations don't relate to one another. I was just looking around. You would sit down with pencil and paper, and you write out approximations that hopefully don't violate any of the physics you care about. That's really important. Once you write out those equations that are approximations to this Schrodinger equation, then you write a computer code, okay? And once you write that computer code that manifests those equations, you tell the computer, you enter that into a supercomputer, and out comes, for example, this. I'll talk about this later. This is an example of an energy distribution, that's what E is, as a function of, in space, as it turns out, okay, as a function of how the nuclei, so the nucleuses of the atoms are moving around. And this little schematic here is showing you where one of the electrons is, that spatial distribution. So just like I said, we get out an energy E, and we get a spatial distribution, this distribution psi. So I have, over the years, developed my own quantum mechanical toolkit. Many people in the audience who are at this conference, of which this is part of this public lecture is a part, also have their favorite quantum mechanical toolkit. But of course, I'm going to tell you about mine. So we have developed accurate yet fast. The yet has to be in there, okay, because accuracy, usually there's a trade-off between accuracy and speed. And so having something which is accurate yet fast and scalable, meaning I can do something big, wave function-based methods for molecules. I'll give you an example of that from biofuels. Sufficiently accurate yet fast. So notice I'm already hedging, okay? But I'm hedging because it's sufficiently accurate for what I'm interested in, namely solids and liquids. So sufficiently accurate yet fast, scalable. Now, instead of the word wave function, I have the word density. So I'm switching from describing the electron positions in terms of wave functions to one in terms of density. I have more to say about that in a minute. And then, of course, you can take the hybrid of the two. Okay? And it turns out that there are certain phenomena and kinds of materials for which that exhibit, for example, this thing called strong correlation or charge transfer and electronic excitostates, these kinds of things, where a hybrid of wave function and density-based theories are necessary to faithfully reproduce the phenomena involved. Professor Rudnick mentioned we also do quantum mechanics-based dynamics and kinetics. I'll give you one example of that. Used to work on, was involved a lot in coupling quantum mechanics and continuum mechanics, solid continuum mechanics, to describe the mechanical deformation of materials. Not really doing that much anymore, but that's my, my toolkit. So let's talk about now different aspects of the energy problem. So there's sustainable fuels, and in this country we made a big bet on corn. There's a lot of discussion about building up a biomass transportation fuel chain. And I want to put big X's through those. Okay? Corn-based ethanol is a lousy fuel. I think it is, as you've already seen, I don't mince words. I think it is not, I think it is unethical to use a food crop as an energy crop. I don't think there's any reason to do that. We have other possibilities. We can use waste from other biomass. We can use potentially plants. I think we should focus on plants that are on land that couldn't be used to grow food. This happens to be camelina. This is algae. There's a lot of work being done on both of these to produce fuels. In particular, algae can produce so-called biodiesel. And so this is, again, from my colleague at Princeton, Ed Law. This is I just love this picture because what it shows is a bunch of different flames. This is standard diesel fuel. This is effectively gasoline. And this is blending in different amounts of biodiesel into the diesel. And what's shown down here are coffee filters. Okay, very low-tech experiment. What it's doing is to collect the soot from the flame. And not surprisingly, standard diesel is the most sooty. And what's very interesting is that if you mix in 10%, 20%, et cetera, of biodiesel, you see you generate a lot less soot, and you're doing it while you're reducing the amount of non-renewable fossil fuels being burned. So I think this is a very exciting direction for us to go in terms of transportation fuels. My role in this is to take our very fast quantum mechanics methods that are accurate, and the combustion to get combustion chemistry right, the level of accuracy is frustratingly important, and to be able to calculate a very good solution for, in this case, this is a molecule, one of the biodiesel molecules, and it's a big molecule. So to do these accurate calculations, typically you could only do calculations on a molecule that's about this size, and we can now do them on molecules even bigger than this by using new techniques that we've developed that are these approximations to the Schrodinger equation. And this is basically, this is where the non-mathematicians can just take a deep breath and forget about this. But this is an expression for a many electron wave function, and we're trying to solve the Schrodinger equation, but the so-called Hamiltonian, this H, is too large to store on the computer, and so you have to have algorithms that involve actually matrix vector products that just give you the Hamiltonian times the wave function, and you use something called the symmetric group graphical approach. That's what SGGA stands for, in order to help you evaluate that matrix vector product so that you don't have to store the Hamiltonian on the computer. But it turns out the scaling of this graphical approach and the operations that go into it scales really badly. It scales as n to the 6, where n is the size of the system. So effectively, that means if I double the size of the system, it means that my calculation costs me 2 to the 6th more. Okay? And so that's 64 times more expensive. So that's not a good thing. So what we have done, and then, so what we've done is to take advantage of what we understand of the physics of the problem to truncate the interactions in different ways and come up with what's called a local correlation method. And so I'm not going to go into the details of this, except to say that we took a method that scaled like n to the 6th. This is time versus size. So here's the time is growing horribly here. And we were able, actually over a number of years, to get the scaling down to linear scaling. Now it turns out, so this was really great, but it turned out that even this linear scaling algorithm was very expensive. It's actually shown here in red, because we then got frustrated about, okay, we're still limited in terms of the size of the system. We can't go beyond 25 carbon atoms. And so, and that's because of what's called the pre-factor for this scaling. And so we implemented what mathematicians know as the Cholesky decomposition, and then that gives us the blue curve. So it turns out the linear scaling disappeared, but now the calculation got really cheap, and we could double the size of the system that we could do, the size of the molecule we could do, without messing up the accuracy of the calculation, which is shown here. This is the energy as a function of breaking a carbon-carbon bond, and just shows that, and this is the blow-up of what's going on down here, and it's within what's called chemical accuracy. And so then we can use this kind of method to calculate the bond, the chemistry associated with a molecule of this size. And that's the kind of thing that we're doing. How does this molecule burn using this kind of applied mathematics? So now I want to move on past fuels to electricity. And we've already talked about the fact that we do have solar, of course, and we have wind. But there are challenges associated with them in terms of both the manufacturing of the solar and the amount of energy it uses, the cost. They're not as efficient as one would like still. Lots of issues like that. This is a picture of a bunch of rare earth elements. You might have read in the paper that, that China actually, I don't know if it's still true, but I think it is still true. The last time I checked, they controlled 97% of the world's supply of them. You could argue that's a national security issue, because these rare earths are used in the motors that run our wind turbines. Okay, so there are lots of challenges, and then there's this issue about the fact that you don't get electricity when the sun doesn't shine. So power oscillates whether it's light or dark outside, and same way with wind, the power oscillates with time if the wind stops blowing. So that's a huge issue. So that's why fusion is so attractive, because once the fusion reactor is on, it can stay on for a very long time, and that's a continuous source of electricity, and you wouldn't need the storage. But there's this huge problem, and this is kind of a cartoon of a damaged piece of a wall, but I have to explain to you about fusion, and I'm going to tell you what the problem is in the context of a project we have going on with the Princeton Plasma Physics Lab, which is one of the premier laboratories working on, a national laboratory working to get us to fusion energy this century. And so the issue has to do with fusion reactor wall materials. And the reason it's an issue is because inside this fusion reactor, actually this is an experiment that has been built at the Princeton Plasma Physics Lab. What you're really trying to do is reproduce the energy of a sun. Okay, of the sun, except you're doing it on a smaller scale than the sun, and so actually it's hotter than the sun. It's incredibly intense. This is the definition of extreme conditions. And so the issue is that the way in which the design of these fusion reactors may be is to use what's called magnetic confinement fusion. It basically stores the energy of the sun, the so-called plasma, in a magnetic bottle. The problem is that the bottle leaks. Well, how does it leak? What comes out are high energy particles, neutrons, tritium, okay? And the problem is that the neutrons, when they come in, this is a picture actually of earlier work that we did looking at a material. The neutrons come in, this is a part of a crystal. In a solid, that's organized as a crystal, all the atoms have their place, okay? They're ordered in what's called a lattice. And so the point is that a neutron comes in, it comes in with so much energy, it knocks an atom out of place. And it creates little vacancies inside this metal. And what it does, so little holes, like little bubbles. And so think about a sponge. Part of how a sponge works is it can take up more water if it has these holes in it, right? And so the neutrons will go and attack any solid surface okay, and will knock atoms out of place and produce a sponge. A sponge for what? A sponge for tritium. And we showed that in some earlier work. And that's a huge problem, because then you're going to end up with something that's going to have a lot of tritium. What is tritium? It's an isotope of hydrogen. And it turns out that hydrogen there are lots of good things about hydrogen, but one of the things that's true about hydrogen, it's the smallest element. It can get out of anything because it's so small, and it makes metals brittle. And so the walls will not survive if they start taking up too much tritium. So what do you do? Well, there's an idea that was developed several decades ago, actually a couple decades ago, to say, well, okay, of course, we shouldn't use a solid. A solid is a problem because of the neutrons. How about using a liquid? Okay. What's special about a liquid? A liquid is disordered to begin with. The neutron comes in and it's not, you can't even talk about it. It's an ill-posed question to say that you're going to knock an atom out of place. All the atoms are out of place. So the neutrons don't do anything. In fact, the beauty of this experiment, which is called LTX, is the liquid lithium experiment. So now every chemist in the audience is horrified, okay, because they know that lithium in contact with water, it's a freshman chemistry demonstration, right? You know, causes fire. So you have to be careful about that. The idea would be, and in fact, the way these would be run would be under high vacuum, and so water will not be an issue. But the idea is to use a liquid lithium wall. That sounds bizarre, right? How can it be a wall? But think about a fountain. You know how you can sort of have these wall fountains that have a solid base and then have a thin film of flowing water. That's the idea of this experiment that's being pursued. And so what we're interested in is understanding how tritium interacts with that liquid lithium, okay? And so but that's actually, turns out, quantum mechanically. Again, I don't want to cheat. I don't want to take information from experiments. So I want to do it all from what we call first principles, just from the basic laws of physics. And I want to use a method where I can really treat the liquid and use lots of atoms. I can't use that method I showed you before that was for the biodiesel molecules. Way too expensive. So I use a density-based method. In fact, I use, Professor Rudnick referred to a density functional theory, but I use a version that was, in fact, the original version that never had a wave function near it, okay? It's called orbital free density functional theory, where all the energy terms, I won't go into the details of this, are expressed in terms of the density rho. And it turns out that I can make that method scale linearly, okay? So that means that when I double the number of atoms, my cost doesn't go up by 64, it goes up by 2. Much better. So we've been able to, in fact, use this quantum mechanics method for up to, actually over 1 million atoms. Not to do interesting science, just to brag, okay? The interesting science we do with of the order of a few thousand or up to maybe 15,000 atoms. You don't need that many atoms, it turns out, to describe many interesting problems. But there might be one eventually for a million. We haven't seen it yet. So I just want to show you something about the accuracy of this method that we've recently demonstrated. And this goes to show, to use quantum mechanics in conjunction with so-called dynamics, meaning that the atoms are moving, because in a liquid, the atoms are moving around. Okay, they're not set in place. And so this is liquid lithium. And the first thing I have to do is prove to the people at the Princeton Plasma Physics Lab that our models, our mathematical and physical models, don't give garbage, right? Really important. So what we set out to do is show, well, how well can we model liquid lithium? And so this is theory versus experiment, saying something very simple. Can I predict the right melting point of a solid piece of lithium going to a liquid? And the way one looks for that, as it turns out, this is looking at the density of atoms as a function, so not the electron density, this is the density of the atoms themselves, so nucleus, the nuclei, as a function of temperature. And what you want to look for is some discontinuous change in that density. And of course, you can see it, right? So I raise the temperature. Right here, here's a snapshot of what is an organized material. This is a solid. And then I get to this temperature, and all of a sudden, boom, the density drops. And in fact, around this temperature, we have a snapshot of what it looks like from the computer simulation. And that's clearly disorganized compared to this. This is a liquid. Okay? And we test this with lots of different ways. But the bottom line is we get a melting point that agrees to within about 10 degrees of the experiment. It's actually too good. Okay? I mean, I'm pleased, but I would have been happy with something even less accurate than that. This is some more equations. This has to do with how where you find the nuclei in this liquid. It's called the pair distribution function. This is called the structure factor. These are measurable. And what you're seeing here, it doesn't really matter. This is a pair distribution function. This is the structure factor. The red is at high temperature, 725 Kelvin. The black is at 470 Kelvin. And there are two sets of data points. One of them is experiment. One of them is theory. And they lie on top of one another, basically. And so it really shows that we have an excellent way of modeling liquid lithium. And we're using this now to look at the incorporation of tritium into liquid lithium surfaces. Because why? It goes back to that slide about why do computation, why do applied mathematics. They can't go in and look. There's no way to go in and look during the fusion and see what's going on. So we need a computer simulation to do it. OK, so I'm going to talk about solar energy conversion. I'll give you just a couple of examples about that. So what's the idea there? Sunlight, lots of energy, and it's going to be around for much longer than all of us. And so the idea is that one should hopefully be able to find some cheap material that can convert sunlight, the energy of sunlight, into electricity and or fuels. That would just be wonderful, okay? So I want to teach you about the phenomenon, about how that solar energy conversion actually works. So the first step is that you take what's called a photon, which is just a little bundle of energy from the sun, or it doesn't have to be from the sun, it's from this too, from any light, so light energy. How do you convert light energy into electron energy? So now I have a picture that shows something different. It shows the energy distribution. Remember that I told you that this Schrodinger equation gives you an energy and a spatial distribution for the electron. So this is now not looking at space, it's looking at energy. And what's really interesting is that in certain kinds of materials called semiconductors, they have all their electrons live in, for example, this set of levels that are called the valence band. Okay, all their valence electrons live here. And then there's this other set of levels, when I solve the Schrodinger equation, or some approximation to it, that's called the conduction band. And at room temperature, there's almost nothing, no electrons that have these energies. And what's really interesting is there's a forbidden set of energies that gives rise to what's called a band gap. And that's critical, because it's so cool. A photon comes in with its energy. It gets absorbed by the material, okay? And if it's the right kind of material with the right band gap, then what happens is it creates an electronic, it excites one of the electrons in the material. And it creates what's called an electron in an excited state, and it leaves behind what's called a hole. It creates what's called an electron-hole pair. Okay, so this is a positive thing. This is a negative thing in terms of sign of charge. And these guys then can move through the material and create electricity. That's how solar cells work, okay? And what's important is that the energy of the photon just has to be larger than the band gap. If it's less, then you don't have enough energy to boost it up here, because there's all these energies here where the Schrodinger equation, quantum mechanics says you can't have an electron of that energy in this material. And so there's, and to make these efficient, it turns out you can get maximum power out of a solar cell when you absorb visible light and no places in the material that could trap those electrons or holes. That's really important. So, I'm going to skip the solar cells because we have them already. I'm going to tell you about where I hope we get fuel someday, so that we stop using corn for fuel and we eventually get it from these photoelectrochemical cells. So this is another picture now of a semiconductor over here and another semiconductor over here that's immersed in a liquid, okay? And it wouldn't have to be. This could be a metal, but it's actually a nice idea to think about both of these being able to absorb light. And so the idea is you have light coming in. You create this electron and hole pair. Because this semiconductor is in contact with a liquid, it turns out that the edges of these bands actually bend, change energy as they approach the interface here between the solid and the liquid. Not important why, but it turns out that holes will drift on this side of the cell, on the anode side, will drift to the interface, okay, and that's a positive charge. And the cool thing about that is it means there's some positive charge on some atom in this semiconductor that is hungry for electrons. And so what does it do? It sees a water molecule, and it strips electrons off the water molecule. And if it does that 4 times, it can make oxygen. And it will make protons, okay, so hydrogen ions, that can be used if I now have, for example, sunlight coming in on the cathode side, where now the electrons get to drift downhill. This is sort of down in energy landscape. Then those protons plus those electrons can be used to take carbon dioxide and make methanol. I mentioned this already. Methanol, again, is a lousy fuel, but it can be converted into gasoline. We actually at Princeton have we have an experimentalist in the chemistry department, Andy Bacarsley, who is one of the first people to show the viability of this. And we worked together on this problem. It turns out, sounds great. He demonstrated it. Why isn't it in, why aren't we using it? We're not using it yet because it turns out that the efficiency is very low. So we have to figure out what's really going on to get the efficiency up to make this viable. And so what we need is efficient, robust, cheap electrode and catalyst materials. And that's going to require, so it turns out the reason, I should say first, the reason that we don't have this happening yet and why we do have solar cells, photovoltaics, is because the properties you need in a photovoltaic are simpler than what's required here. And the difference is you got to do chemistry here, okay? And that chemistry actually requires that the energy of the electron in the hole be at certain energies that allow a chemical reaction to proceed. And I'm going to show you an example. I think I'm running out of time somewhat, so I'm going to skip to this and just show you an example of that. So this is a kind of a shortened version of this. You have light hitting a semiconductor, the semiconducting material. I have my valence band and the edge of that valence band. I have the conduction band and the edge of those states. And I form an electron-hole pair. And the energy of the hole has to sit below the energy that's designated by this horizontal line of this particular reaction that will take water to oxygen, so to oxidize water, or to take, and then the protons that are formed, the electrons from here need to be at an energy high enough above the energy that's required to take electrons and protons to make hydrogen. Notice that the sum of these two gives you a water splitting reaction. You may have heard about that people are very interested in having ways of using sunlight and materials to split water to make hydrogen and oxygen. Oxygen's great. Why do we want hydrogen? A lot of people will say we want hydrogen for fuel. I personally am opposed to that. I think that, and for practical engineering reasons, hydrogen, though, we need hydrogen. Because we need renewable hydrogen like this. Why? Because right now, all hydrogen comes from fossil fuels. That's bad. Why do we need hydrogen at all? The chemical industry uses hydrogen all over the place, and if we're going to use, for example, biomass to create fuels, it turns out there's a lot of hydrogen used in converting biomass to a viable fuel. And so it totally defeats the purpose if you use hydrogen to hydrogenate the biomass if the hydrogen came from fossil fuels, right? So what we want to do, we need viable ways to split water to make renewable hydrogen. And that's something that I also work on. And then this is an example, again, of the energy being higher than the energy that's required. You have to have enough excess energy, some excess energy above the energy required to take carbon dioxide to methanol, for example. So one thing you can ask yourself is how nature does it. Because in fact, in every plant, and this is a little cutout of what's called the oxygen evolving center inside what's called photosystem 2, PS2, which is the engine behind, it's at least part of the engine behind all of photosynthesis. And it's so funny, because what I've done is to cut out this little tiny part, and there's enormous other parts of the protein that I'm not showing you, okay? Why? Because I want to zero in on the active ingredient. And the active ingredient is this little cube. And this cube consists of manganese, calcium, and oxygen. Those are the elements. And so I'm not a biochemist, and I look at that and I get afraid, and I think, you know, I want, I'm joking, but I want to see if I can simplify things. And I also don't want to just mimic a plant, because in fact, plants are not very efficient. You think, well, gee, we should just mimic plants and mimic photosynthesis. But it turns out that the efficiency of photosynthesis in plants is only a few percent. And we know that's not good enough. We need to be up around 20%, okay, efficiency. And so, we have to do something different than what plants did. Plants didn't care about efficiency. They cared about staying alive. That was their goal, right? So what I said is, let's look at that and think about an inorganic analog, okay? So not a plant, but think about manganese oxide itself, okay? So this is just manganese and oxygen 1-to-1, very similar to what it looks like there. There's a crystal that looks like this, and that sounded like a good idea. The band edges are placed such that these reactions could happen, but the band gap is too large. Why do I say too large? How could it be too large? It only absorbs ultraviolet light. Why is that a problem? Because if you look at the distribution of energy that the sun gives us, if I say the only light that can be absorbed is ultraviolet light and higher, which is what I would have to do because anything smaller than ultraviolet light wouldn't get absorbed, my efficiency, my upper bound on the efficiency of that device would be 2 or 3%. I'd be back down to where the plants are. That completely defeats the purpose. And it would be much worse than that, because there are many other ways to lose efficiency other than just the band gap. And so we asked the question, could we take this material and mix it up with other elements, alloy it, to see whether or not we could reduce the band gap into the visible? And so, in fact, we showed that you can. So these are the gaps. It doesn't matter. But the point is they start out in the ultraviolet, and you get down into the visible. So it's possible through computation to make suggestions. This is the example of suggesting a target, to say, let's go into the lab and try to make that material, if possible, and see whether or not it can have the ability to do this kind of so-called photocatalysis. I think that I should wrap it up. Is that, Russ, where are you? Yeah, pretty soon. Right. OK. So I am going to skip ahead a little bit. It's a typical thing that scientists do, and mathematicians do, is that they want to tell you so many things that they absolutely don't get. They absolutely end up with way too many slides. So that's because we're all very enthusiastic. Okay, so I'm going to stop by just giving you my vision of where I hope everyone in this room will contribute to, and everyone watching, hopefully streaming live on the internet, will think about what you can do to be a part of the solution so that we can leave the planet for future generations in much better shape than it is right now. And so that includes energy efficiency of buildings, for example. And that's one of the very first things we should be doing. Of course, we have solar and wind now. We need to make the solar more viable economically, mostly. We have electric vehicles. I think one could ask the question, why do you need fuels at all? right? If you can just electrify the vehicle fleet. Of course, the problem here is cost and range, as you know. And so a lot of these things right now, you could argue do exist. What doesn't really exist is a viable path to electrify our airplanes beyond some demonstrations, I think, because it would require batteries of such a level that it really would be impossible. And so thinking about biofuels or fuels from sunlight, which is shown here, this is actually from the National Renewable Energy Lab. These bubbles are hydrogen, okay? So it's a potential source of fuel. Light shining on this, splitting water. Then, different sources of renewable fuels for aviation, I hope, will be able to displace petroleum eventually. And then ultimately for electricity, I hope we are able to, within a few decades, see demonstration and ultimately commercial fusion reactors all over the planet. So with that, I have to thank my research group. And this is just the current incarnation. It would be absolutely impossible for me to be up here talking to you at all without having had just absolutely fantastic students, both at UCLA and at Princeton, who have made this work possible. And so I also need to thank all of these acronyms, which are my funding sources from the federal government. And I thank you very much for your attention. I'd be happy to take questions.
Thank you, Emily, for that wonderful talk. And we have time for some questions.
I happen to be treasurer of the Green Party of California. Can you imagine a fuel that is approximate to not natural gas, which has very high phase change, but anyway, there is a fuel that is very simple. The gasoline we buy is whatever garbage they want to sell us. If they're selling jet fuel today, then the gasoline you put in your car is a different molecule. If it's coming from a different raw source, it's a different molecule. It's extremely difficult to take an internal combustion engine and decide how to burn that, as some of your demonstrations here. But liquid ammonia, and we sold 6 billion gallons to each other last year, is a very effective fuel in internal combustion. In fact, the US Army were burning their turbines with liquid ammonia. So can you look at that?
Well, certainly it could be looked at. What I would say is that I think people have great concern that we need to save our nitrogen for growing food. And so using it as a fuel, because it is the source of fertilizer, okay? So using it as a fuel, really I would look at as having the same problems as using corn for ethanol. So while it certainly can be used as a fuel, there's no question about it. It's exothermic to burn ammonia, so you get energy out. I don't think that's the solution.
Yeah, UCLA grad school graduate, physics. Your discussion about the problems of fusion, which I think is in fact the answer, and focusing on the wall problem is not anything I've heard of, and your discussion from metals to liquids. Have you heard of liquid metal?
Have I heard of liquid metal?
Yes.
Yeah, this was a liquid metal. I mean,
No. It's a solid material that's made by a company called Liquid Metal, LQMT. And what they do is they take a metal and they melt it down and they quench it right through the phase transition so that you have the properties of metal with zero, what do they call it, mold, or molding.
I know what you're talking about. You're talking about metallic glasses. That's what you're talking about.
Metallic glass.
Yeah.
Have you looked at that?
I personally haven't. Certainly people have. And the thing is that, right now metallic glasses have niche applications. And I doubt that it would be useful for the fusion wall reactor, for the walls of the fusion reactor, because I think I'm really guessing here, okay? But my my instincts are that it will take up tritium rapidly, okay? Because it's disordered and it'll have defects in it, and that's where the tritium likes to go. So I don't think that's going to solve the problem, unfortunately. Oh, hi. Gil.
How much do you think nuclear reactors will give us lots of energy in the future? I mean, I think in France about 75% of the electrical energy comes from nuclear power.
Almost all of it does. Actually, it's higher than that. Yeah. Yeah, I mean, that's, so we have people, so it was mentioned that I direct a center at Princeton, the Andlinger Center for Energy and the Environment, and we have people that work on aspects of both nuclear energy policy as well as nuclear reactor design. And I think, you know, in that regard, what is of interest to me is these so-called small modular reactors, which you've probably heard about, which are, the issue there is, so they're sort of like, another way they've been described as nuclear batteries, that you essentially have a reactor in a box and you bury it. And it's not, you know, it would be impossible for somebody to convert that into weapons grade material, for example. And once it finished, you would just take the box out and transport it to where you were going to store it. I mean, the open issue right now, I think, in terms of traditional nuclear power, is deciding about risk management of the nuclear waste and the technologies associated with the nuclear waste. So, yeah. You want to follow up? Sure.
Well, yeah, in France, they're doing a lot of work to build a new type of reactor that uses already created fuel and ends up giving you something. They get 100 times more energy out of it, and it what's left over has a short lifetime and can't be used for weapons. It seems to me that pushing in that direction is really important.
Right. There's a number of technologies people are looking at, and I have tried to be agnostic on that slide. I think that, you know, aside from the food versus energy issue, I think that it could very well be that we cannot ignore implementing more nuclear power in order to reduce the carbon dioxide. I hope it will be a bridge, right? And that we will be able to take them offline as soon as we have fusion. So.
Let's take a few more questions.
There's questions over there.
How about here?
I'm concerned about the problems of rare earths being used in electric cars and the sustainability in that direction. Is there a life cycle sustainability analysis of, say, diesel, you know, modern diesel cars that get 45 miles per gallon versus the electric cars that require mining of these rare earths? And is there a program to recycle the rare earths from these cars? What are you aware of in that direction?
Well, there seems to be quite a bit of evidence that there has been a lot of environmental ramifications to the mining in China. And so it's a big problem, and it's good that you brought it up. I think that you know, I really do believe that if proper regulation is put in place, there are ways to mine responsibly, and just like to hydrofrack responsibly. I don't know. There may be life cycle analysis and that has been done on that, making those comparisons. I can't help you with that. I'm sorry.
Let's take one more question. Here?
Yeah.
Down in front.
This might be a stupid question.
There's no stupid question, as I used to say here at UCLA.
So the photoelectrochemical cells,
Yeah.
they were using like water, and a lot of like this stuff uses water. So isn't water like a finite resource?
So you brought up a very important point, and it's something people are very concerned about, which is that there's often a trade-off between energy and water. Almost every energy production, conversion process that one has involves water. Even standard power plants have cooling water, massive amounts of cooling water. And so you're right, it's a serious concern. And that's why on the slide that I had with all of the, hopefully, solutions, there was, I didn't talk about it, efficient water desalination, as another goal that's really important. I think if we can desalinate seawater without using an enormous amount of energy, which is how we currently do it, then it won't represent a problem.
So is it not going to be finite anymore? Because, like...
Well, it's finite, but it's a very large finite number.
Okay.
Let's thank Emily for a really thought-provoking and wonderful
I hope it's what we have.